If you saw a giant isopod without context, you would probably assume it belonged in a horror trailer rather than a biology textbook. It looks like a pill bug from a backyard stone, enlarged until it becomes vaguely mammalian in scale, plated in armor, pale as old bone, with a face that seems built out of pure indifference. That visual shock is exactly why the animal became famous online. But the deeper reason people stay obsessed with it is not the way it looks. It is the way it survives. Stories circulate about giant isopods going for astonishingly long periods without eating, about individuals hauled up from deep water that did not instantly die, about an animal that seems to ignore the ordinary rules of metabolic urgency. As usually happens, the internet turns a real biological story into a supernatural one. The reality is more precise and, in some ways, more impressive. A giant isopod is not breaking the laws of thermodynamics. It is revealing what evolution can do when the most valuable trait in an environment is not speed, beauty, or aggression, but ruthless efficiency over very long stretches of scarcity. To understand why giant isopods seem almost absurdly durable, you have to start with what they actually are. They are crustaceans in the order Isopoda, which makes them relatives of the woodlice or pill bugs many people know from gardens and damp soil. The resemblance is not superficial. The segmented body, the many similar legs, the hard exoskeleton, the basic architectural plan are clearly shared. The difference is that the deep sea took that familiar design and pushed it toward a radically different way of life. Some species in the genus Bathynomus can grow past 30 centimeters, and a large specimen has a presence that feels much less like an insect and much more like a heavily armored machine. That size is part of what makes the animal memorable, but size alone is not the point. In the deep ocean, food is patchy, unpredictable, and often separated by enormous distances in both time and space. A body built for constant activity would be a liability there. The giant isopod succeeds because nearly every part of its biology is tuned to a world where the next meal may arrive late and without warning. That is the real context behind the famous starvation stories. A well-known aquarium giant isopod in Japan went years without accepting food, and the case became a media sensation because it sounded impossible. But impossible is the wrong word. In cold, dark habitats, where energy is scarce, metabolism slows, movement becomes economical, and the difference between life and death often comes down to how long an animal can coast between opportunities. Giant isopods are not living on nothing. They are living on stored energy, on reduced activity, on a physiology shaped by an ecosystem that punishes waste. Deep-sea animals frequently show this kind of extreme thrift, but giant isopods display it in a particularly visible way because their body size makes the contrast feel so dramatic. We instinctively associate large bodies with high intake and constant fueling. A whale must eat heavily. A running mammal must keep feeding. A giant isopod reminds us that those expectations are specific to certain environments, not universal laws of life. Pressure is another place where the animal seems to defy common intuition. People often imagine any deep-sea creature will explode, collapse, or liquefy the moment it is brought upward. Some animals really are extremely sensitive to decompression, especially if their bodies rely on gas-filled spaces. Giant isopods do not have a swim bladder. and that matters. A body made mostly of tissues and fluids responds very differently to pressure change than one containing compressible gas pockets. That does not mean a trip to the surface is harmless. It means the dramatic movie version of instant destruction is not a good model for every deep-sea organism. Giant isopods can tolerate changes that would be catastrophic for many fishes. And their robust exoskeleton adds another layer of physical resilience. The shell is not magical armor, but it is a rigid external framework that protects soft tissues and supports a body designed for a high-pressure, low-energy existence. The animal looks crude, but that crudeness is exactly part of the design logic. Simplicity in extreme environments is often a kind of sophistication. Then there is the question of why these animals are giant in the first place. Deep-sea gigantism is a real pattern. In the deep ocean, some lineages produce forms that are dramatically larger than their shallow water relatives. Scientists do not think there is a single universal cause. Lower temperatures, slower metabolisms, delayed maturation, energy storage advantages, and ecological pressures all likely play a role. In the case of giant isopods, large size may help them survive longer between meals and travel efficiently across sparsely rewarding seafloor landscapes. Bigger bodies can buffer scarcity. They can also make an animal less vulnerable to some predators and better able to exploit large but rare food falls when they do occur. It is tempting to treat gigantism as if the ocean simply dialed everything up for spectacle, but that misses the point. Size is useful only when it fits the math of the habitat. In the deep sea, where feast and famine can be separated by long, empty intervals, a large, patient scavenger can be an excellent solution. Calling giant isopods scavengers is accurate, but incomplete. They are famous for feeding on carrion because dead whales, fishes, and other sinking bodies are among the most important resource pulses on the deep sea floor. When something large reaches the bottom, mobile scavengers may arrive quickly, guided by chemical cues diffusing through the water. Giant isopods are part of that response network. Yet they are not just passive janitors waiting beside a cosmic trash chute. They can investigate living prey, tear tissue efficiently with strong mouthparts, and compete aggressively when food appears. What looks from a human distance like laziness is actually strategic restraint. In a habitat where unnecessary motion wastes precious energy, inactivity is not failure. It is discipline. The animal is not built to perform. It is built to remain viable until a rare opportunity appears, and then to exploit it with brutal efficiency. Even the way giant isopods molt reflects that same cautious engineering. Many crustaceans shed an old exoskeleton all at once, which briefly leaves them soft and vulnerable. Giant isopods often molt in two stages. First the rear portion, and then, after some time, the front. That split process reduces risk. An exoskeleton is not just a suit of armor. It is also an anchor point for muscles and a structural necessity. To lose all of it at once in a harsh environment would be dangerous. A two-step molt is a way of distributing vulnerability rather than absorbing it in one catastrophic interval. It is the biological equivalent of avoiding all-or-nothing bets. When you look at enough details like this, a pattern emerges. Giant isopods are not merely animals of the deep sea. They are animals whose entire way of existing assumes that stability matters more than speed, and that the safest path is usually the one that minimizes exposure. Their reproduction follows the same logic. Females brood eggs in a specialized pouch, and the eggs can be remarkably large for a crustacean. Large eggs mean more developmental resources per offspring. In difficult environments, that can matter more than producing vast numbers of tiny, poorly provisioned young. Juveniles emerge at a more advanced stage than many people would expect, which reduces the danger of sending extremely fragile early life stages into a world that offers little margin for error. Harsh environments often favor reliability over extravagance. Giant isopods do not represent a frantic strategy of reproducing as much as possible and hoping a few survive. Their lineage reflects the opposite principle. Invest in offspring that are better prepared from the beginning, because the environment is too unforgiving for wasteful odds. The senses of a giant isopod are also better understood as deep-sea tools than as crude leftovers from an ancient body plan. On the seafloor, at great depth, vision is often limited or nearly useless, while chemical and mechanical information become critically important. A scavenger that can detect faint traces of organic decay or subtle disturbances in the water has a serious advantage. When a carcass reaches the bottom, it may create one of the few genuinely rich food events in a landscape of scarcity. Arriving early matters. Giant isopods do not need theatrical intelligence to succeed there. They need sensitivity tuned to rarity. The deep sea often rewards animals that are specialists in noticing unusual events, and giant isopods appear to be exactly that, patient detectors of infrequent opportunity. It is also worth remembering that the deep sea floor is not a single flat wasteland. It is a mosaic of sediment plains, slopes, variable currents, oxygen gradients, and differences in how much organic matter reaches the bottom. Giant isopods are part of a broader recycling system that helps break down dead material and move nutrients back into ecological circulation. This makes them more than a curiosity. They are participants in the ocean's slow accounting. When a large animal dies and sinks, scavengers and microbes together transform that body from isolated biomass into shared resource. Without that work, the chemistry and food flow of the deep ocean would look very different. The giant isopod may appear grotesque to us, but in ecological terms, it is not a mistake or an afterthought. It is one of the reasons deep ecosystems continue functioning. None of this means the animal is invincible. Giant isopods can be preyed upon. They are vulnerable during and around molts. They depend on temperature ranges, oxygen availability, and water quality that fit their physiology. In captivity, they may die for reasons that are invisible to people who assume a tough-looking body can tolerate anything. There is a difference between being resilient and being unkillable, and giant isopods live squarely in that difference. Because we still observe so little of their natural behavior at depth, myths quickly fill the gaps. They become immortal monsters, proof that deep-sea life exists outside normal biology. But the truth is better than the myth, precisely because it is more specific. The giant isopod is not beyond nature. It is a superb expression of nature under constraints that most humans never have to imagine. That is why the animal stays with people once the initial disgust fades. It forces a revision of what success looks like in biology. On land, we often equate success with speed, constant activity, rapid growth, visible dominance. In the deep sea, another equation can prevail. Win by enduring. Win by spending almost nothing when nothing is available. Win by turning patience into anatomy, metabolism, behavior, reproduction, even the timing of your own molts. The giant isopod is unsettling because it makes that alternative strategy visible in a body we can immediately compare to a familiar backyard creature. It is as if the planet took a humble design, sent it into darkness for millions of years, and asked what would happen if survival itself became the main art form.
The answer is not elegant by human standards.
It is better than elegance. It works. Researchers are still learning basic things about these animals because the deep sea is expensive to visit and difficult to watch continuously.
Much of what people think they know about giant isopods comes from snapshots, baited cameras, trawls, occasional submersible observations, aquarium cases that may not perfectly represent wild behavior. That uncertainty matters. It is one reason exaggerated claims spread so easily. A dramatic story can occupy the space where long-term field data should be. But the gaps are scientifically productive as well. Every time giant isopods are observed feeding, moving, molting, or brooding, they refine a broader question about life in extreme habitats. How much can metabolism slow before it stops being compatible with active animal life? What body plans are especially good at surviving pressure, scarcity, and cold? What trade-offs become acceptable when the environment rewards endurance more than innovation? So the best way to look at a giant isopod is not as a monster, not as a meme, and not as an impossible animal. It is a carefully tuned answer to a brutal set of conditions. It shows what happens when evolution has millions of years to optimize for rare meals, low temperatures, high pressure, and long, uneventful stretches between moments that matter. The result is a creature that seems emotionally wrong to us because we are built for a different world. We are adapted to notice motion, urgency, hunger, reaction. The giant isopod belongs to a realm where life can be measured in waiting, where thrift is a superpower, and where a body that appears primitive may actually be one of the most disciplined designs in the ocean. Once you see it that way, the animal stops looking like an absurd exception. It starts looking like one of the clearest demonstrations that evolution does not care whether a solution flatters our imagination, only whether it survives.